Okay, so as stated in an earlier video, when we differentiate the exponential or the natural exponential function, e to the power of x, the derivative is equal to e to the power of x as well. Now this is really, really useful because it means that we can actually differentiate any function that has a function of x within the exponential using the chain rule. Okay, so what we're going to do is we're essentially going to have a go at differentiating this using the chain rule of differentiation, because if we substitute this value up here with a u, and then we know how to differentiate e to the power of u using a similar line of logic on the left there, but this will allow us to do it for any function involving e that we'd like. So let's have a look at some examples. So our question is to use the chain rule to differentiate y is equal to 3x plus 4, and then y is equal to e to the ax plus b. So what we're going to do is we're going to say, well, let's let u be equal to 3x plus 4. And that means that y is going to become e to the power of u. So dy du is equal to e to the power of u. So remember, we get the same function back. Okay, and then du dx is equal to 3, which is just the derivative of u up there. So what I should do is I should actually write it this way. I'll just leave it like that for now. Okay, so remember that the chain rule dy dx says that dy dx is equal to dy du times du dx. So what we can do is we can substitute those dy du and du dx into this. So dy du is equal to e to the power of u, and du dx is equal to 3. So this is the same as 3 times e to the power of u times 3, which is equal to 3 eu. But we don't want dy du, we want, not dy du, we want dy dx. Okay, so what we need to do is we need to resubstitute that e, or the u, back in. And remember, u was equal to 3x to the power plus 4. And so we get this as our function. Now what you'll probably notice, or possibly notice, is that the derivative of this inside came out to the outside. Just like when we do a square root function, or square root of a linear function, the derivative comes to the outside. So what we can do is we can actually generalize this. And we're going to generalize this by doing this function here. So y is equal to e to the ax plus b. So again, we're going to start off by doing a similar thing. Let u be equal to ax plus b. So that means du dx is equal to a. This is going to give us y is equal to e to the power of u, which in turn means that dy du is equal to e to the u. Again, because the derivative of e to the power of u is just e to the power of u. So using the chain rule, dy dx is equal to dy du times du dx. So this chain rule using dy du, which is e to the power of u, I'm going to times that by a. Okay, and so this generalizes our function as a e to the u, and by resubbing u, that's going to give us a e to the power of ax plus b. Okay, so that's what dy dx is equal to. And this works for all functions. So remember, it's the derivative of this inside, and it comes out the front. Okay, so what we can do is we can use this as a generalized form. Okay, so the generalized form is, okay, so if y is equal to e to the ax plus b, then dy dx is equal to ae to the ax plus b. Now, what this also means for us is that we might not, or we shouldn't now use e as a place value or as a holder or as for a substitution, because e has actually been associated with a number now. Okay, so whenever we want to use an algebraic substitution, we're not going to use e anymore because e is effectively a number. So what you'll notice is when I do my algebraic substitutions, I'm going to leave out e whenever I do it. So if I start from A, I'll go A, B, C, D, and then I'll go straight to F. So we'll leave that E out. Okay. So with that newfound knowledge, what we can do is we can find the derivative of some functions very, very quickly. Okay, so in this one, we've got A, which is y is equal to e to the 7x minus 4. So the shortcut says find the derivative of the power and then put it down the front. So dy dx is equal to 7e to the 7x minus 4. That's it. Okay, b is a little bit trickier. We've got y is equal to 9e to the negative 2x. Okay, but we're going to do the same thing. We're going to take the derivative of the inside and bring it to the outside. So dy dx is equal to, so it's going to be minus 2 times 9e to the minus 2x. Okay, so minus 2 times 9 is minus 18. So the derivative is minus 18 e to the negative 2x. Okay, same thing for this one as well. Okay, so y is equal to e to the power of a half x minus 6. So in other words, we're going to say what we want. This is the same as a half x minus 3. So dy dx is equal to a half times, because remember we're taking the derivative of the inside and bringing it out to the outside, a half times e to the half x minus 3, or in a simpler form, e to the half x minus 6 over 2. Okay, so that's just simplifying it out a little bit. So that's the end of the differentiation of exponential functions. It's actually quite simple to do. Okay, so it's just take the derivative of the inside and put it, or of the power, and bring it to the outside or out the front. So with that being said, that's going to be the end of the differentiation video, and I'll see you guys in the next one when we look at some tangents.